Thanks for the introduction. My name's Kay Osterhout, and I'll be talking about a project to re-architect Spark so that it's easier to reason about performance. This is joint work with a couple of other folks at UC Berkeley, including my advisor, Sylvia Ratnasamy. First, a little bit about me. I'm a PhD student at UC Berkeley, where my thesis work centers on understanding the performance of large-scale distributed systems like Spark. I've done work both to measure performance of systems like Spark and things like the project I'll talk about today, which is thinking about how we could build systems in a way that makes it easier to see what's going on. I'm also a Apache Spark PMC member, and my work on Spark has focused on improving the scheduler. A little bit about what you can expect from this talk. This talk is a forward-looking view of how we might build systems like Spark in the future, or how you might look at building a new system sort of similar to Spark. We do have an implementation, and it's API compatible with Spark, so that means that you can run existing workloads that run on Spark unchanged on top of the thing that I'll present. But it's a very major change to the internals of Spark. It's about 20,000 lines of code, and as a result, this is not something that you can expect to be merged into Spark anytime in the near term. Okay, so let me get started. So let me talk about what it might look like when you run a Spark job. So an idealistic vision of what it might look like if you run something on Spark is that you have a cluster of Spark machines, and there's a user who has some job she'd like to run. She submits the job to the cluster, she gets some results, and Spark runs the job very quickly. And this is maybe how some past systems looked, like if you bought a database from Oracle and you had some specialized hardware and that database had been engineered to run very quickly, you would submit your job, it would run fast, and that would be the end. The system is something you could treat like a black box. But increasingly, that's something that's not true today. So this is a very idealistic view. More typically, what it looks like when someone runs a Spark job is that the user runs the job on the cluster and she's not satisfied with the runtime. So maybe she's running this job on EC2 and she upgrades to using some beefier machines, maybe machines that have some more disks. Then maybe she does some profiling to understand her job and decides to change the job that she submits a little bit so that the code is faster. And then maybe she also changes some of the configuration parameters of the job based on the performance that she's observed. So what this view looks more like is that a user runs the job, they get some understanding of the performance of their job, and they use that to change the way they're running the job to make it faster. So the takeaway here is that to get good performance on systems like Spark today, users need to be able to understand what's going on so that they can make appropriate choices about how they'd like to run their job. So how easy is it to do this today? Last year at Spark Summit, I gave a talk about measuring Spark performance. And what I showed in that talk is that there had been a long history of work optimizing the I/O for systems like Spark. There had been a lot of work on optimizing the disk and network use of these systems. What I showed in that talk is that when we added a bunch of instrumentation to Spark, what we found is that actually CPU and not I/O was typically the bottleneck. One result that I talked about in that talk was that for the workloads that we looked at, optimizing the network performance could improve the job runtime by at most 2%. So this was one piece of evidence that there wasn't a very strong understanding of the performance characteristics of jobs run in these systems. So that was last year at Spark Summit, and since then there's been a bunch of work on Spark. In particular, there was this Project Tungsten initiative from Databricks that looked at optimizing the CPU time of Spark. This is a blog post about Project Tungsten, and while I'm sure you can't read these highlighted sections, what they're saying is basically that the project is optimizing the CPU time, and this project was based in part on our measurement study showing that CPU was the bottleneck. So that initiative started about a year or so ago, and we're on the cusp of Spark 2.0 being released. And there's some evidence that in Spark 2.0, we're back to this regime where I/O is again the bottleneck. There's a paper from some folks about this that will be appearing in Hot Cloud this year. So the takeaway here is that both we don't have great ways to understand performance, and performance is evolving over time. So let me just quickly recap what I've said so far. First, for systems like Spark, users need to be able to reason about the performance of the jobs they're running, and doing this is very difficult. And perhaps most importantly, these bottlenecks are constantly evolving as software and hardware change. And as a result, I would argue that this is something that needs to be sort of always on. When a user is running a job, she needs to be able to reason about what the performance bottlenecks are so she understands how to speed it up. So with that, I'd like to present a vision for how Spark might look in the future. So here's what a future Spark UI might look like. And the top part of this probably looks familiar to those of you who have run Spark before, but some of the things on the bottom are different. So first of all, the job is reporting the performance bottleneck. So here the job is reporting that it was bottlenecked on disk, and that if you improve the disk throughput by 23%, then the job would be bottlenecked on something else. The UI might also report a couple of other things, like it might report some non-bottlenecks. Here, this job is not bottlenecked on the CPU, and it's not bottlenecked on the network. So if you wanted, you could downgrade those components of the system without sacrificing any performance. The UI might also report suggestions like caching the input data in memory, and it could tell you what the possible improvement would be if your data were stored in a deserialized in-memory format. And then finally, I think perhaps the most useful part of this is that the UI could have a predictor, where you could plug in the characteristics of a different cluster with some different number of cores on each machine and different I/O resources, and the UI would tell you an estimate of how quickly your job would run. What I'm going to do in the rest of this talk is I'll talk about how we might be able to achieve this vision. So to do that, I'll start by talking about Spark, and I'll describe a little bit about how Spark works to describe why it's difficult to reason about performance of Spark jobs today. Next, I'll present this new architecture for how we might build systems like Spark in the future called Monotasks, and I'll describe why using Monotasks makes it easy to reason about performance. And then finally, I'll show some results from what we can do when we have Monotasks and use it to run jobs. So first, let me give some background about Spark. This may be familiar to some of you. So let's say you have a very simple Spark job. This is a Spark job that starts by reading some remote data, it filters the records, and then it writes the result to disk. The way that Spark works, and actually the way that most of these systems work, this is also how systems like Hadoop work, for example, is that they begin by breaking the job into a bunch of parallel tasks. And each one of these tasks does the same core computation, but it does so on a different piece of the input data. Then the Spark scheduler will assign each one of these tasks to worker machines. So here in this example I've shown, there's a couple of workers. And in Spark, each worker has some fixed number of slots that it can run tasks in. So here, each of these workers is running 4 concurrent tasks. And when the tasks complete, the scheduler assigns some more. Now let's zoom in on what one of these tasks look like. So this particular task is reading some input block over the network, it's filtering it, and it's writing the result to disk. And what happens when this task runs is that it begins by reading a little bit of input data over the network. And as soon as it's read some input data, it starts computing on it. Then it continues to read more data in the background over the network. Once it's done computing, it will write the result to disk. And it continues to pipeline the reading, computation, and writing to disk of the results for the entire job. So the important part of this picture is that the job is parallelizing the use of a bunch of different resources while it's executing, and it's doing so at very fine time granularities. Now let me talk about why this makes it difficult to reason about performance. So if you look back at this view of what a task is doing, one thing that makes it difficult to reason about performance is that this task is bottlenecked on different resources at different points in time. At the beginning of the task, it's bottlenecked on the network. At the end of the task, it's bottlenecked on the disk write. And then in the middle of the task, this task is bottlenecked on the CPU. So even if you ask a simple question like, what's the bottleneck, there's not an obvious answer for this task. So this is the first challenge, is that there's many resources in use, and different resources may be the bottleneck at different points in time. Now the second challenge for running things like this is that there's all of these tasks running concurrently, and they're sharing many of the same resources. So if you look at a particular point in time, all of these tasks are bottlenecked on the network, but it might not be because they have a significant demand for the network. It might be that they're contending for the network, because there are a bunch of tasks that are all using the same resource at the same time. So given this complicated decomposition of what it looks like when you're actually running a task or running a job with Spark, what can we do to understand performance? And as I mentioned, I gave a talk about this last year at Spark Summit, and the big takeaway from that talk was this technique called blocked time analysis, where what we did was we added a lot of instrumentation to Spark, and this allowed us to answer questions like, how fast could a job complete if a particular resource were infinitely fast? So I just want to emphasize that this is a pretty simple question. This is an upper bound on if the disk were infinitely fast, how fast could the job complete? And answering this question was the result of about a year of adding instrumentation to systems like Spark. So this is one piece of evidence of how hard it is to answer these sort of simple seeming questions about performance. I just want to belabor this point a little bit by going back to that example of the job and asking you all to think for a minute, if you wanted to make a prediction, like how much faster would this job complete if I had twice as much disk throughput? How might you be able to do that? If you start thinking about what this would entail, you would have to walk through each of these tasks at the granularity of each of these pipelined reads. And for each one of the disk writes, say, okay, how much would the time for this disk write have changed? And how would it have affected the way the different tasks contend for the disk? And then how would that have affected the way that all of the other resources are used? And you can see that pretty quickly this becomes much too complicated to be possible to do. So to recap, there's a couple of challenges to reasoning about performance in systems like Spark. First, tasks are using many different resources. Second, multiple tasks are running on the same machine, and they have essentially unregulated access to the different resources on that machine. And finally, a consequence of these first two challenges is that there's no simple way to model performance of one of these jobs. So with that background, I'd like to talk about this new architecture of monotasks that presents a different way that you might architect a framework like Spark. So here on the left side, I've shown the three challenges that I discussed with Spark, and I'll talk about how Monotasks addresses each one of them. So first with Spark, I mentioned that tasks bottleneck on different resources that they parallelize the use of. This is the first key idea in Monotasks, is that each task uses exactly one resource. So if you go back to that previous Spark job that I talked about, this job that reads some remote data, it filters the records, and it writes the result to disk, here, instead of decomposing the job into these tasks that use many resources, we'll decompose the job into tasks that each use one. So there will be a bunch of network resources that each read a block over the network. There will be a bunch of CPU monotasks that each do this filtering for one block. And finally, there will be a bunch of disk monotasks that each handle writing one of these blocks to disk. So what this does is it means it's very easy to reason about what each one of these tasks is doing and which resources it's using. It's only using one resource, and it's using that resource for the entire time that it's running. The second problem I mentioned with Spark is that concurrent tasks may be contending for the same resources. What we can do with monotasks is, because each task uses only one resource, each resource can be controlled by a dedicated scheduler that's responsible for running all of the monotasks for that particular resource. So here's all those monotasks I showed earlier, and each type of monotask will be scheduled by its own scheduler. So there's a network scheduler that might schedule one monotask at a time. One scheduler that's maybe easiest to think about is the CPU scheduler that can run one task per CPU core, or the disk scheduler that can run one task per disk. And because of this decomposition of monotasks, it's very easy for the schedulers to maintain high utilization. Because the disk scheduler, for instance, knows that when it starts a task on one of these disks, that task will use the disk completely until it finishes. The final challenge that I mentioned with Spark is that there's no model for performance. With this monotasks decomposition, you can trivially model the performance of a job. So the first step to modeling the performance is to compute the ideal runtime on each individual resource. So I mentioned that there's all of these CPU monotasks. To compute the ideal CPU runtime, you can take the total runtime for all of these CPU monotasks and simply divide it by the number of cores that are present in the cluster to get the ideal CPU time. You can do the same thing to compute the ideal time for the network and then for the disk. This is something that you can do based on the measured runtimes you have after running a job like this once. Then once you have this, the job runtime is simply the maximum of any one of these ideal runtimes. One nice thing about this is then it allows you to also very trivially answer questions like, how much faster would the job be if it had twice as much disk throughput? Here what you can do is, instead of dividing those disk monotask runtimes by 2 for the 2 disks, you can divide them by 4, and you can compute here the new job runtime. Had this happened, this particular job would have now been bottlenecked on CPU instead of on the disk. So to recap, here on the left side is what things look like with Spark, where there are a bunch of tasks that parallelize the use of many different resources, and this makes it difficult to reason about performance. On the right side, we have what things would look like with monotasks, where each task uses only one resource. Each resource is regulated by a dedicated scheduler, and this allows us to create a simple model for jobs performance. Now, one final question you may be wondering is, how can you actually do this decomposition? I said at the beginning of this talk that this project is API compatible with the existing Spark, and you may be wondering how it's possible to do this without requiring a user to do a bunch of additional work to break their job into these monotasks. So it turns out that this is something that we can do entirely under the covers in Spark without telling the user. So if you have this original Spark task that pipelined a bunch of different resources, what we do with monotasks is we basically rip out the execution engine of Spark to instead break this task into a bunch of monotasks. where first we do the network read, then separately we do the filtering using the CPU, and then finally we write the output to disk. And we enforce hard dependencies between each of these monotasks so that, for example, when that CPU monotask starts, we know that it will be able to run to completion without having to wait for any of the data over the network. So the implementation of Monotasks is API compatible with Spark. What this means is for the workloads that we ran on Monotasks, we ran them unchanged on top of Monotasks from their original implementations, which were written to use with Spark. Another important point about the implementation is that Monotasks works at the application level. So we're not changing the operating system to, for example, go in and change the OS disk scheduler to be aware of how Spark is scheduling disk tasks. Instead, what we're doing is we're finally controlling the things that we give to the operating system to do. So for example, we're only giving the operating system one CPU-intensive thread to run per CPU core and counting on the fact that the operating system will, for the most part, schedule things in the way that we expect. So I've talked about Monotasks, and now I'd like to talk about some results from what happens when we run Monotasks with some different workloads. So the first, and perhaps for some of you, most important part of this talk is like, did I just make Spark a lot slower? You know, we undid this fine-grained pipelining, which has often been seen as the kind of key performance technique that's been used by Spark and most previous systems that have looked similar. So first I'll show some results showing that the performance is on par with Apache Spark. This is the results of running the Big Data Benchmark, which is a SQL workload that's sometimes used to benchmark systems like Spark. And here what you can see is there's 2 bars for each one of the queries, one showing the performance of Monotasks, and then the Monotask bar is blue on the right, and then the performance of Spark is shown on the left. And what you can see is for some of these queries, Monotasks is a little bit faster, and for some of them, Monotasks is a little bit slower. But overall, the Monotask performance is not significantly different from the performance you would get from running Spark. Here's 2 more workloads that we've run using Monotasks, a sort workload and a matrix workload that involves doing a bunch of matrix multiplications. For these workloads, I've broken down the changes in runtime by the stages of the job. So the left bars show each stage and how it varies for Spark and Monotasks, and then the rightmost set of bars is the total runtime. And what you see here is that Monotasks is faster than Spark, and the reason here that Monotasks is faster is that it's able to better utilize the underlying resources because of those per resource schedulers. It can get higher resource utilization. So this is the sort of base result showing that we didn't make Spark a lot slower, but the important part of this project is seeing what we can do with it. So let me talk about 2 of the sort of cool things we can do once we have this decomposition. First, that we can model performance of jobs, and second, that the framework can actually leverage this added clarity about performance to do its own optimizations. So first, let's return to this question that I talked about a bunch at the beginning of this talk. Let's say I ran a job and I wanted to know how much faster it would run if I had more I/O resources on the machine, if each machine had 2 disks instead of 1. So this is a sort workload that we were running on 20 machines on EC2, and the left bar shows the original performance with Monotasks, where we were running on machines that each had 1 disk. The middle dark blue bar is showing the prediction from Monotasks. Based on the runtime of that original workload, how fast did we predict it would run if it had 2 disks? And then the final rightmost bar is the actual runtime when we ran it on a different set of machines that had those 2 disks. The high-level takeaway here is that we're able to fairly accurately predict the runtime on the new machines. In all cases, these are 3 different workloads shown along the x-axis. The predicted runtime is within 10% of the actual runtime on the new cluster. So this is close enough that it's a meaningful estimate. If you're thinking about buying more expensive hardware, for example, that it's giving you some sense of how fast it would run. The other important thing to note about these numbers is that doing this prediction isn't trivial. So you'll notice that the speed up from adding another disk is not the same for these workloads. For that leftmost workload, the CPU was the bottleneck. So there was essentially no change in runtime from adding the disks, and Monotasks is able to correctly predict that. The right 2 workloads are a little bit more interesting. For both of these workloads, the disk was the bottleneck, but adding twice as many disk resources didn't cause the job to go twice as fast. The reason was once you added more disk resources, something else became the bottleneck. In this case, the CPU became the bottleneck. And as a result, you get somewhat less than a 2x speedup, and this is something that Monotasks is able to correctly predict. Another question that we're able to predict is how much faster would a job run if the data were deserialized and in memory. This is something that's often tricky for folks to reason about because storing the data in this format involves 2 changes. First of all, you're eliminating the disk time to read the input data from disk. And then second of all, you're eliminating some CPU time to deserialize the data from these byte buffers into a bunch of Java objects. So in order to answer this question, you would have to measure a couple of different things. And let's just look at, again, what that might look like in Spark. So here's that Spark task. If you wanted to measure the time the task spends deserializing data, this would involve making many measurements throughout the lifetime of the task. These are measurements at smaller granularity even than the granularity at which this I/O pipelining occurs, because Spark uses this decades-old Volcano operating model where for each record it does all of the computation on that record. So for each record it would first deserialize it, then it would do whatever computation the job is doing, and then it would serialize the results. As a result of this, measuring this overhead is much too high to do at the application level. And by the way, there have been some projects that claim to do this, and you should be very skeptical of them, because if you do them, it adds very significant overhead to how long it takes the job to run. So doing this is essentially impossible to do at the application layer if you wanted to do it for things like Spark. With Monotasks, on the other hand, what we can do is we can sort of unroll this deserialization. Instead of pipelining it with the rest of the computation, because we're already unpipelining everything, we can also unpipeline the deserialization. So we could do all of the deserialization at the beginning before we begin computing on the data. And as a result, it becomes possible to measure how long this takes. So to return to this question, how much faster would the job run if the data were deserialized and in memory? With Monotasks, this involves two steps. First of all, we use the model to eliminate that disk monotask time. And then second of all, we have these measurements of how long it took to do the deserialization, and we can use that to adjust the CPU time and then rerun the model to see what the bottleneck resource is and how long the job would take to complete. Here are some preliminary results with doing this on one particular workload, where again, the original runtime where the data is serialized and on disk is shown on the left. The predicted runtime is shown in the middle, and then the actual runtime running on deserialized in-memory data is on the right. And what you see is that Monotasks is again able to accurately predict the runtime using a totally different data input format. The final result that I'd like to talk about is how the framework can leverage this performance clarity to improve performance. So one thing that's cool about Monotasks is that each one of these resource schedulers has complete visibility over how that resource is being used. And as a result, there's some new opportunities for the framework to do optimization based on the queue length for each of these resources. So in particular, one thing that I'll talk about today is that the framework can configure the number of concurrent tasks for the best performance. For those of you who've been using Spark for a while, one thing you may have noticed is with Spark, you can set the number of tasks that run concurrently. So here's a graph showing the result of a sort workload, and the left set of bars are all different configurations of Spark. So that leftmost set of results is Spark with 2 concurrent tasks per machine, Spark with 1 task per machine, the next one is Spark with 2 tasks per machine, and so on. And what you can see with Spark is that it matters how you set this particular configuration variable, because depending on the characteristics of your workload, it might be optimal to run more tasks, for example, if you want to take advantage of a bunch of I/O resources, or it might be advantageous to run fewer tasks if there's not very many CPU cores on the machine and your job is very CPU intensive. With Spark today, this is something that the user has to tune manually. With Monotasks, the schedulers have enough information to make this decision automatically. Like the CPU scheduler knows, for example, that it has 4 CPU cores and that it should only be running 4 CPU tasks at a time, and it will automatically run the workload with the correct degree of concurrency. This is reflected in the results here, where you can see that Monotasks is faster than any of the configurations with Spark. This is an ongoing project, and there's a couple of avenues of future work that we're looking at. The biggest thing is how we can leverage this performance clarity to further improve performance at the application level. Just to give you a sense of something else that we're thinking about doing, one of the things that you can do is you can notice when the network scheduler is idle and use this to opportunistically start prefetching data that needs to be used for future jobs. Another thing that you can do for Monotasks, much easier than you can do with existing systems, is to automatically configure for multi-tenancy. So because of this thing that I mentioned, that the resource schedulers know the correct concurrency, it's easier to run multiple workloads concurrently, because you don't have to do this fine-tuning of user A needs to use half of the cores on the machine and a third of the disk resources, and user B can use the rest. Instead, the schedulers can figure out how many resources need to be assigned to each job automatically. So just to recap, I started with this vision of what Spark might look like in the future, where the UI reports metrics to users on every job about what the bottleneck is and what they might do to improve their job's performance. Then I talked about why this is very challenging with the existing architecture. To realize this vision, I presented Monotasks, where we decompose jobs into these units of work that only use one resource and that can be each scheduled by a dedicated resource scheduler. And then I showed how that can be used to construct this trivial model for a job's completion time. If you're interested, or if you have a particularly challenging job where you're having trouble reasoning about the performance, I would love to hear more about it, and please feel free to email me. And with that, I'll take any questions.
Thank you. I may have a kind of a general question. I have two very big RDD. For example, I want to join them together. For example, I have RDD1 with 1 terabyte data, and RDD2 also has 1 terabyte data. For example, I want to join by user ID. So, do you have any suggestions to optimize the join, make it join quick and better? Thank you.
Yeah, so the question is on join optimizations for two different RDDs. Usually the best way to optimize this is to just store the input data in memory, or to use a different storage format for your data is often something that will end up helping a lot.
There are 1 terabyte, too big.
Yeah, I see. The data is 1 terabyte, so too large to store in memory. Yeah, so with a job that's that simple, there's often not a lot that you can do to optimize the job with Spark. Usually changing the data format to eliminate some of the serialization time is one of the best things that you can do. Yeah.
Hi. I would like to know, are you not considering any other file system other than HDFS? We have GPFS also, which is a spectrum scale, which is a centralized storage. In that case, you won't have a single disk, or a node disk is not attached to any of the nodes. It's a centralized disk. In that case, how can you actually assess the requirement of the disks and the write?
Yeah, so the question is, what if you're using some other storage system, like some centralized storage system that's doing its own management? And this is something that we see in practice a bunch with the workloads that we run, where things are stored on S3, which is basically a black box for us.
Okay.
And yeah, it's true that if you wanted to use something like that, you would either need a scheduler for that storage system that's sort of doing things in the way that we would expect, or it doesn't work.
Okay, one more thing. Did you not consider anywhere the memory configurations?
Yeah, exactly. So the resources that I talked about are all resources that are shared in time, whereas memory is shared in space, which means that it has slightly different sharing properties. So in the schedulers actually take the memory usage into account in slightly different ways, where it means the schedulers will reprioritize monotasks. So one example is if the disk scheduler has a queue of read and write monotasks and the memory is starting to fill up, it will prioritize the write ones over the read ones. But basically we can treat memory somewhat differently than these other resources.
The reason why I'm asking is currently the trending is going on for the memory with the FPGA technology. So you can just put the card and you can read some flash disk, and you can just consider that as a memory also, which can go up to 40 terabytes of memory also can be optimized. Take an example of IBM has introduced CAPI, which is a FPGA card. If you put that all 40 terabytes of a flash disk can be turned into a memory. So while considering that, can you just, I just want to know the little more tasks also. Just keep in consideration. It'll be good for us also, and it's a very good suggestion. Thanks.
Yeah, thank you.
Okay. When you consider the monotask, you show that the performance compared to the original one is just plus or minus 10%. But what is the worst case scenario? Because you are getting rid of some sort of fine grain pipelining. So can you talk about some worst case?
The question is the worst case scenario. So there's sort of two bad scenarios where monotasks doesn't do well. The first is where you have a very small number of tasks. So if you only have one wave of tasks, so say you had 10 slots in your cluster and you're only running 10 tasks, then the fact that we've undone this fine-grained pipelining within each task ends up being a big performance problem. And so if you had an original task that was well bottlenecked on all of the resources and you only had a few, then monotasks can be 2 to 3 times worse than Spark. Luckily, what we've seen is that as the task launch overhead for Spark has become smaller and smaller, people tend to already run many more tasks than there are cores on the cluster, so that doesn't typically tend to be a problem. The other scenario where we see that the performance is quite a bit worse than Spark is where the original Spark workload is taking significant advantage of the buffer cache. So oftentimes, your Spark job will write a bunch of output, and you're writing it to HDFS, for example, to disk, but it's actually all hitting the buffer cache on the machine. With monotasks, we always force everything to disk because we need to be able to schedule the disk the way that we want, essentially. And so as a result, if the workload originally was using the buffer cache and now we're forcing things to disk, then it can take a bunch longer.
Yeah, here, over here. So does this produce any profiling report on, let's say, a test run, so we could then reason about how we should provision for CPUs or I/O capacity?
Yeah, so that's sort of exactly what this should generate, is as soon as you've run your job once, it generates all of the information that you would need to predict the runtime on any kind of new different cluster.
It feels like your approach to distributed computing is almost the diametrical opposite of what I heard in the keynotes this morning, which is we're going to give you an amazing new black box, you use our APIs, and we'll take care of performance for you. And you're saying let's build tools to empower people to understand performance. Can you talk at all about ways in which the perspective you're putting forward might have a place in the larger Spark community or the larger Spark ecosystem?
Yeah, this is a good point. Many of the newer developments on Spark have been, how can we provide a better API so that users have to do less? I think one argument you can make is that developers will always, whoever is making that API still needs this information in order to sort of optimize the API to work well. But I would also argue that even with a great API, today's users have so many choices. Even if the system doesn't let you configure anything or doesn't let you change your job, you still have to decide what kind of machines you want to run on. And it's no longer this one-time decision of I'm going to buy a bunch of machines that I have for the next 5 years. It's like EC2 has 20 different instance types, and which ones do I want to use? And even in that regime, you need some understanding of which ones that you want to choose.
Right here. This sounds like a natural evolution of the way work is scheduled on tasks. So is this going to make it into Spark Core?
Yeah, that's a great question. Is this going to make it into Spark Core? And I think that depends in part on how much appetite there is for having this from folks in the community. So TBD is how I would answer that.
My question was partially stolen. I was going to ask about the path to integration. Is there any way, so you're saying that if we hit the buffer cache, you can't really leverage the improvements. In fact, it hurts you. And part of the main offering of Spark is that it allows you to take advantage of the cache to speed up operations. Is there still space for this within kind of the internals? So the scheduler, the shuffle, where this can be put to use, but to still kind of allow you to leverage memory to speed up your computation?
Yeah, so I guess the distinction that I would make is you can still use the cache when data is explicitly cached. The only time when you can't take good advantage of the cache is when the data is getting implicitly cached because the user has written it to disk, but there's enough space in the OS. It's actually easier in Monotasks to do things like store shuffle data in memory because you just have better information about what's going on. And you can do some sort of neat optimizations where you're smart about which data you write to disk. Like if only half of your shuffle data is being written to disk, you can kind of intelligently choose which half. So it's the half that's going to be used later in the job. Rather than the approach in Spark right now is basically like throw it in the buffer cache and hope that if your data is small enough, it will stay there and that otherwise things will be sort of okay.
One other quick question. To what extent will this help with debugging when your job fails and one obscure task fails for an unknown reason?
Yeah, there's some categories of debugging that this helps. Like some of the kind of weird things happen sort of debugging that we've seen happen where like something crazy goes on with the network. And with Monotasks, you could say something like, okay, there was some other user running and their tasks were using up all the network resources and that's why your task had a timeout. There's other categories of debugging that this doesn't necessarily help, like something in your code crashed, and there's still various memory issues that are tricky to debug with Monotasks, just like they would be in Spark. Cool, thanks.